Okay, screen is shared.
Yes. One of the last to do is to allow your video.
Oh yeah. There we go.
And your audio.
Oh, it's the wrong one. Can link.
Yeah.
Okay.
Thank you.
And audio is also Camlink.
Yes.
Okay.
Is it just one?
It's on. Yeah,
Thank you.
it's on. Here. All right. Welcome back. So after the brief crash course in meteorology, primarily the first two parts of the lecture, we are now getting more into the machine learning aspects. So luckily, only a few of you raised your hands when I asked you about your expertise in machine learning. So I won't be embarrassed to teach you a couple of fundamentals here. But we'll actually start with a comparison of machine learning versus numerical modeling of air quality, weather, and climate. So we'll actually continue a bit with the classical approaches to weather forecasting and science. So the structure of this lecture is first the forecasting problem in very simple words, then a couple of aspects of numerical modeling of weather and climate, in particular in terms of discretization, types of forecasting, and just one slide on data assimilation, so that at least you've heard about that concept. Then a bit the potential of deep machine learning in weather forecasting, and then I will go through a couple of architecture concepts just to, I mean, again, this can't replace a full-blown lecture or introductory course of machine learning, of course, but just to give you a tiny bit of understanding in terms of how these things are related and what machine learning in principle can do and why and how. Okay, so let's start with the forecasting problem. So in principle, what we want to do if we forecast the atmosphere, if we forecast weather or also climate or air pollution, is we have an initial state x of t, of time t, and we want to find basically the solution or the state at the time t plus delta t. And this already tells you that we have that we are using a time discretization, because in principle, of course, time is continuous. But in modeling, we always split time into discrete time steps. So we have discretization here. The other discretization that's very important in numerical modeling of the atmosphere is the spatial discretization. And in principle, what you do is you cover the Earth's surface with a grid. And then you also do that vertically. So you basically have then a couple 100,000 or so grid boxes spanning the planet. And in each of these grid cells, you have to solve in the end hundreds of equations, not all of them differential equations, that you have to solve at every time step. So we heard about the momentum, energy, mass conservation equations, but then of course there's all kinds of other things dealing, for example, with physical processes like the formation of clouds or evaporation of clouds, rainfall and whatnot, diffusion and stuff like that. And you can imagine that if you have something like 100,000 or 1 million of grid boxes and you have these kind of number of equations, and you need time steps of, say, 10 minutes or so to do a reasonable forecast of the atmosphere, that this takes quite a bit of computational power to actually solve these models. And indeed, weather forecasting models are one of the most demanding applications for supercomputers today. And the meteorological community is still one of those who is always asking for more. So currently they're aiming to get to resolutions for global forecasts of 1 kilometer. And this really requires sort of exascale computing systems, so next generation computers.
What do you think about this IBM? I think it's a weather prediction at 1 kilometer forward.
Yeah. I mean, you mean the weather, the machine learning based one, or?
Yes.
Yeah, we will come to that.
Okay.
You're jumping it. So errors in such modeling comes from spatial temporal discretization. Errors, basically, because you are averaging, of course, somehow over these regions, these boxes. And the other big source of errors is the so-called empirical parameterization of unresolved processes. So you can imagine, and current resolutions of weather models are something like 10 to 30 kilometers. And as I showed you earlier in the scale picture, this basically has sort of just an envelope over convective systems. And so therefore, everything that happens in detail in like a convective cloud or so needs to be defined in a so-called parameterization. So there's some empirical laws that, for example, if you have so and so much so-called convective available potential energy, then the cloud will rise so and so higher, and that kind of stuff. So that's basically a typical parameterization. And they are uncertain, and so this is where errors come from. And I'm sort of spoiling the show a little bit in the sense of arguing already here that this is sort of where the large potential of machine learning lies, in the sense that if we are running these numerical models, we are sort of coming top down. So we have this general understanding of the atmosphere given through these physical equations, and we sort of then, and those work very well. But then we have a hard time getting down to the subscale processes and getting those right. And then due to the coupling of the different scales, this generates errors that can proliferate. Machine learning sort of has the opposite approach, in the sense that you're data driven. The data will somehow implicitly contain information from all these scales. Yeah, so if the machine learning model is able to use that information, you might sort of overcome that problem of resolving the small scales. But on the other hand, you have a much harder time figuring out the general, let's say, physical laws behind the atmosphere. And so there are some approaches also, so-called physics-based machine learning or so, where you try to combine them together. So I showed you this image of grid boxes, and indeed there are several ways of how you can define these grids. I don't want to go in much detail here, but let's say the classical easy one would be the latitude-longitude grid. Well, you can imagine that the lines become thinner and thinner, or the boxes become thinner and thinner as you approach the poles, and that indeed leads to instabilities and problems of the model. So there's a so-called Courant-Friedrich-Levy criterion, which in a nutshell tells you that within one time step, your air mass should not travel further than across the grid box, one grid box. And so, because otherwise you get into numerical instabilities. And so you can imagine if you have that grid on the left, because you basically have to define your time step in a way that it's still capable of solving for the smallest grid boxes near the poles. So you need rather small time steps in order to achieve a stable model. There are some ways to overcome this. So for example, people have come up with a reduced grid where towards the poles, you simply reduce the number of grid boxes, make them larger. And of course, you can imagine, I mean, in terms of data processing, this has some implications. So typically you will then interpolate the values near the poles and spread them again on a equirectangular grid. Or, and this is a more modern approach, people have come up with models that use different geometries, so not basically squares, but rather triangles, for example, so-called icosahedral grid. This is used in the new model of the German Weather Service, for example. So it's called ICON for icosahedral numerical model. And then you can basically divide these large triangles into smaller triangles and thereby get to different resolutions. You can even so-called nesting, use different resolutions in the same model run. So you can focus on in one region and have run that with finer resolution. And these kind of grids, of course, avoid the pole problem. On the other hand, and this, of course, should be well known to all of you working in like geoinformatics, and so you have more difficulties in terms of let's say defining the relations between grid boxes and in terms of the memory layout and storage layout, and so that's more complicated than if you have these kind of regular structures there. Vertical discretization. So somehow you want to define the levels in the atmosphere. The naive approach would be just to say, okay, let's do whatever 10 meters, 50 meters, 100 meters, 200 meters, and whatnot above above sea level. But then you have some mountains reaching into the grid boxes, so you would end up with some grid boxes having missing values because there's a mountain and no air. Now, and this creates problems then in terms of getting the dynamics right, so the wind flow and stuff like that. And so what people came up with is this so-called hybrid sigma grid, where in the lowest levels you have a so-called terrain following coordinate, which is relative to the surface pressure. And then towards the upper atmosphere, you switch to a simple pressure grid where you have constant pressure levels. And the implication of that is that the actual altitude of these layers really changes every time step, because it's based on pressure, not on altitude. And that's just something to be aware of if you work with this kind of model data. And here's just a cartoon. I find that quite helpful to really be clear about that. So how does the real world look like versus the model world? So in reality, of course, we have sort of slopes and all kinds of small little ditches and other stuff on the Earth's surface. In the model grid, which is rather coarse, you basically have constant altitudes in every grid box, and also kind of mean properties of land surface. Not quite true yet, so there are some sort of mosaic approaches where each of these kind of boxes is split into different land surface types, and then afterwards they're aggregated together to formulate the exchange with the atmosphere. But at least you have kind of a somewhat weird perception of reality, in the sense that you have sort of discrete changes in the landscape. Now let me get to different types of prediction and different types of modeling. So here's, in a nutshell, the difference between weather and climate modeling, or as people say, weather prediction and climate prediction or projection. And the point is that in meteorology, you use observational data to obtain the initial conditions of a numerical simulation. And the forecast range is then typically hours to weeks. So that's weather prediction. Whereas in climate, you have an unconstrained model. So there's no initial state from observations. Although that's not quite true, there are now projects where, for example, you want to start a model run from ocean observations, because the ocean is very slow in getting right, basically. The model is tuned to avoid a biased drift under constant climate conditions, and then you start changing boundary conditions, like, for example, the CO2 concentration, to then observe what happens. The prediction or projection range is then typically years to centuries. And then on the bottom, I list the difference between a prediction and a projection. So a prediction is a forecast that's based on a clear expectation of the future. So you kind of think you know what's going to happen in terms of, for example, if you make a forecast for the next 10 days, you don't expect that, whatever, a volcano will erupt or something else, an asteroid will hit the Earth or so, but conditions will stay as they are. Whereas if you make a projection, so for longer time scales, then you need to define a scenario. So you need to formulate your expectations, what will happen in the future. So typical case for climate simulations is that, I mean, how much emissions will the different countries put into the atmosphere over the next, whatever, 100 years or so. And then physically speaking, there's a difference that then relates to the modeling. Between the initial value problem and the boundary value problem. So that basically the same what I just said in a somewhat different view here. So if you're on shorter time scales, then a model is really mostly driven by the initial value. Where again, to some extent, linking back to the autocorrelation I mentioned earlier. So basically, if you know the initial state of the atmosphere very precisely, you can make a pretty good prediction of what will happen in the next hours. Somewhat less good prediction what will happen over the next days, and at some point this really breaks down. So typically, let's say after about 7 or 8 days, now you're losing a lot of your forecast skill. So your skill scores will become negative if you paid attention. And then if you go to very long time scales, then you have a boundary value problem. So this is kind of the scenario thing. So if you don't have a good estimate of how the system or how the drivers will change, you can't make a good prediction. And then there's this difficulty in between here, and that's sort of the research field of decadal predictions, which are actually among the most difficult things you can do in meteorology, because you're just in the middle between boundary and initial value problem. All right, now a little bit on data assimilation. So how do people actually find the best initial state for the model forecast? And this is done through data assimilation. So basically, what you do in more sophisticated data assimilation, there are all kinds of different concepts you can use called Kalman filter and 3D var and 4D var and whatnot. So this is just a very generic idea about the 4D var assimilation, where you are following basically the trajectory of the model for a given time step, and then you make a correction to the observations at that time step. And then you basically run backwards again. So in a way, you run backwards and forward until you sort of match the trajectory of the reality of the real observations. And then from then on, you run your forecast.
Machine learning to do that.
You can also use machine learning to do that. In fact, yeah, right. That's actually one of the most promising applications of machine learning. Right, and one thing that's kind of neat to see for machine learners is that indeed what you do in data simulation is you minimize the cost function. So that's a concept that's very well known to machine learners. Minimization of the cost function is exactly what you do there as well. Point is that here you are specifically taking into account the errors. And there are two different errors. So basically the summation term here on the left-hand side, you see the background error. So this is the model error. On the right-hand side, you see the observation error. So you need to know basically the quality of your observations to really get a good adjustment of the system. Okay, now we finally really get into machine learning. But before we do so, let me sort of define the problem anew. And this is that something we sort of pondered a little bit about in the sense of if you now come with a new tool, machine learning, to the old field of weather forecasting, then of course you have a very hard time as a newcomer to beat these systems that have been developed over decades and all these evaluation systems and stuff like that that's been going on. And we kind of figured, well, let's actually think about what is actually happening in numerical weather forecasting or in real weather forecasting. What is the end goal? And the end goal is not the model result, but is really to get a good forecast at a specific location. And so, for example, I mean, just in terms of looking at products from the German Weather Service, you will have warnings for floods or again floods or avalanches. You will find time series at specific locations. And so in the end, what people are interested in to find precise local information. Yeah, so we've just had that brief discussion in the coffee break that some people here want to get like make, for example, temperature forecasts for specific fields or so for a farmer. So on. That's the scale where really in the end the people are interested in. And that's
If you have a good model, then you make the good predictions. So.
Yeah, but not on those scales. That's because, I mean, if you have a weather model on like 3 kilometer scale, you can't make a prediction for 100 for a 2 hectare plot or so. Yeah, so that's really where you're still missing a lot. But that's, I think, important to understand because I guess initially there was this kind of competition of machine learning with actual weather models, and you can only lose. But if you're looking at the end product that you want to achieve, there's actually a lot of potential. Because you're basically directly focusing on the scales that matter. And so that prompted us to sort of reflect a bit about what is it actually weather prediction and how can you use AI? Well, in principle, if you reformulate the forecasting problem that we had at the very beginning, you can actually say that what you want to do is a mapping of some state of observations. So from this global observation system that I showed you earlier, including satellites, sons, station measurements, to specific end user forecast products. And this can be like a hurricane track, this can be a temperature field, this can be a warning or whatnot. And then we're actually finding that indeed this is something that's precisely what machine learning does. Yeah, so machine learning does nothing else than finding a functional relationship between input data and output data. And so that's basically where the potential of machine learning lies in the field of weather forecasting. Okay, but now we take a step back and think about how actually numerical centers like the ECMWF, they've of course also thought a lot about the potential of machine learning, and they identified many aspects where machine learning can help in the, let's say, current workflow of weather prediction. What you see here is the 4 boxes are basically covering the classical flow of observations to products. So you have the observations, they're being processed and whatever smoothed and bias corrected, whatnot. You have the data assimilation step that I briefly showed to you. You have the actual numerical weather forecast, and then in the end, you need to do post-processing and dissemination to really get to this kind of local level forecast or statistics or whatnot. And then around all that, there's sort of a 5th layer, which is the actual high performance computing and big data processing infrastructure. And also there are ideas where machine learning can help a lot. And so there are these several things, like for example, for observation processing, machine learning could improve the automatic quality control of analysis. It could do anomaly correction. Then in the data assimilation, you can do this sort of precondition, as it's called, bias correction, model learning, use of land surface observations, gap filling, mapping of non-Gaussian to Gaussian distributions for the assimilation, such things. Then in the actual modeling, you can, for example, replace certain components of the model, like hydrology models. Then also things for the sub-grid processes, clustering, categorization of predictability. You can emulate radiation, so that's something that has been already quite successful. You can do gravity, wave drag, so also certain different parameterizations. Or you can directly learn forecasts from observations. And then in post-processing, there are other things like sort of downscaling, feature detection, precipitation post-processing, and stuff like that. And then finally, for the sort of, let's say, technical aspects, you can optimize data access. So let the machine learning model learn basically the access patterns to your observation data, for example, and then optimize that. Climate lab, I don't really know what they meant with that. Anomaly detection, this kind of stuff for workflow for IT infrastructure. So that if you detect certain patterns in the workflow that sort of what's it called, slow down the system, you can try to do that. And also things like very technical, optimize the chillers for an HPC system. So depending on the workload. All right, and now we will go through, actually not really fundamentals. What's that? Oh yeah, sorry, part 3, correct. So we will go through some fundamentals of machine learning to give you a little bit of glimpse of the available, let's say, technologies used there. We'll start with the random forest. That's something that many, let's say, Earth scientists or remote sensing people are quite familiar with. So in a nutshell, the idea is that you grow a set of random trees, and random trees are decision trees, where basically at each node you take a decision, yes or no, or smaller or larger, or something like this. And then you accordingly branch into the next branch. And then there may be another decision following, or you are at an end node, a so-called leaf. And by basically doing a bootstrapping, so by taking out a certain proportion of your data and resampling, you generate a whole set of these trees, a whole forest. And then in the end, you basically take a majority vote of most trees say this is the result, and so that you accept that as a final result. Yeah, and programmatically, it's basically a whole set then of if then else statements that sort of generated by these trees. The other, let's say, very fundamental concept in machine learning is the so-called perceptron. And here you basically have different inputs, x1 to xn, and it's based on basically a neuron in the brain. That's the fundamental idea. Perceptron also already dates back to like 1950s. And the idea is that you first collect all the inputs and weigh them by weighting factors. And these weighting factors are what you actually train, what you optimize. to then make a prediction. But before you make the prediction, you will run the result through a so-called activation function that basically allows you to distinguish between a 1 and a 0, so or 1 and -1. And that's then the output. There's one important aspect that one needs to keep in mind, and that's a so-called bias correction, basically. So you will always add an extra node here, x0, sometimes it's called b, which always has the input value 1 and which has an additional weight that you also train, and that allows you to basically shift your decision point a bit to the left and right. So the concept, as I said, is basically collecting the weighted inputs, apply a nonlinear activation function, and this nonlinearity is very important for the power of the thing. And then the result is the output, right? And you're training basically the weights in an iterative loop. Next step are multi-layer perceptrons or feed-forward networks. And here what you do is multi-layer perceptron already says it. You basically combine a lot of these perceptrons together. So not only horizontally, so basically you allow, similar to random forest, basically several perceptrons to work on the same input data, but also then you stack several of these layers on top of each other. And in the end, you generate the output. Yeah, so it can be a few or many layers that you stack together, and important is that you only allow forward connection. So every layer of this multi-layer perceptron only sees basically the results of the layer before. There's no, let's say, reverse flow. The reverse flow only is used basically in the back propagation. So basically for adjusting these weights, you will sort of traverse in the reverse direction of the network. And then you optimize your weights. One thing or a few aspects to remember, so that you use different loss functions. We briefly had the concept of loss function in the data simulation. So it's the term that you want to minimize in order to between basically the labels, so your truth and the prediction of the network. And you use different loss functions, whether you are working on a classification problem, for example, rain, no rain, versus a regression problem, for example, the amount of rain that's falling down. So typically for classification, you will use, what's it called again, log, softmax, oh, typo here, and a linear layer for regression, right? Yeah. Okay, then people have come to recognize that sequence processing, for example, time series of atmospheric variables, require something else, because the classical MLP or FFN does not memorize what was going on before. Sorry. So every time step, you will just sort of run afresh. You have new inputs and you just run it through your model. You make a completely independent prediction. And in order to account for autocorrelation, basically, you can couple cells together. You basically add a hidden state as a memory into the system. And that allows you then to take into account basically the results from the preceding step into your new prediction. This concept has been developed primarily first for language processing, but of course can be used in other areas as well. So yeah, I already said the main thing, that you have this kind of hidden cell, and then you can stack together several of these cells. So depending on the sequence length you want to analyze. And there are different variants of this. So let's say easy one, recurrent neural network, just has really one hidden state that you memorize. And then the more sophisticated ones, so-called gated recurrent units or long short-term memory cells, where you have 2 or 3 of these hidden states inside, and then certain functions of how which of these influences the prediction of the next step. To say already that the disadvantage of these is that you have a fixed sequence length. So in this case, if you have, for example, 5 cells, you can treat sentences or time series of 5 points, nothing longer. There's a clear limitation there. Right, now I forgot to mention that on the top, I always did a little bit of a classification. So most of these are actually from this Towards Data Science web pages, where some of these concepts are explained either in very easy form, so easily understandable. Here for the recurrent, I've found it more okay reading. So if you come up with a better page, let me know. I can replace that. And sometimes I also find them actually very good and also detailed, these kind of web pages. All right, so this was in terms of time series. The other thing that are important, in particular, if you look at the kind of data we are interested in now with weather and climate data, we have not only temporal relations, but also spatial relations. And this is where convolutional neural networks made a big breakthrough in the 2010s around. So the idea here is really a classical image filtering concept, where you have so-called filter kernels. And these kernels, so that's the kind of red numbers that are moving around there. They sort of extract certain features from an image, let's say. And this is basically done by doing a matrix multiplication. And so the point in terms of machine learning is that what you're learning is these kernel weights. So rather than having a prescribed 101, 010, 101 here, these numbers would actually be learned through the training process. And then you basically, typically in a CNN network, you will combine several of these layers. So there are different steps. This is the actual convolution step. Then afterwards, you will run this through an activation function that's typically shown together. And then afterwards, you do a pooling step, which basically combines information from several cells into one. So the most common one is max pooling. So you will, for example, average 4 neighboring cells and just use the maximum value of these 4 cells. And that then proceeds and proceeds. And typically what you see then is that initially, you start with a relatively small stack of these filters. So you might apply, for example, 8. And then progressively, we'll get more and more of these different filters, which are supposed to basically extract more and more different features from your original data. And then at the very end, typically, depending a bit on the application, you will then add a fully connected layer to basically produce your output. This could be like image classification, something like this. One more thing I'd like to mention here is that in terms of activation functions, I didn't go into detail here. There were classical ones used in the perceptron, like a 10H or sigmoid function, so rather smooth functions going from -1 to 1. Whereas in convolutional network, it turned out that so-called ReLU function, which is basically 0 for negative numbers, and then just a simple linear function for positive numbers, actually works best and avoids sort of gradient problems and that kind of stuff. So here's in a bit more detail. One of the things, student quiz, so just to keep your attention awake. So what we saw is if you apply these filters to an image, you will actually reduce the image size. So in this case here, you have a 3x3 filter. These yellow boxes applied to a 5x5 image, and the result will be a 3x3 image. So the question now is, if you had a filter like a kernel of 9x9 pixels, how much pixels would you lose of the original image? How many pixels?
It's a quadratic
relationship.
Yeah. So 4.
It's 4 on each side. Yeah.
Yeah.
Exactly. So 8 in total. Yeah. Mm-hmm. Okay, let's move on. So encoder decoder architecture. So in principle, what was going on in the CNN network, let me briefly come back to this again. So where you basically have this compression of information by doing the sequence of convolutions and max pooling, and you basically generate more and more or wider stacks with little pieces inside, basically. So you can almost imagine this would be something like a token for features in the image. So this can then be used in so-called encoder-decoder architecture. So the first thing is really that. So it might be, for example, a CNN stack. And then in the middle, you have sort of the representation layer or the encoding vector, or also called bottleneck, which is really where your information is encoded. And then you expand that again to reproduce an image. Sounds a bit silly at first, but the point is that you're basically using now self-supervision to train or to learn this encoding vector in the middle. So to basically find out what's the relevant information in your data. So one example is you can, for example, in training, you could just basically try to generate the exact output image that you feed in for the input. And then afterwards, when you're done and the network knows how to do that, you will basically take away that decoding part and replace it with something else. So for example, then for image recognition, you could then attach a feed-forward network to it and train it separately. Or there are other applications, like, for example, denoising of images. So if you have a rather noisy image, Thomas will love it. You can basically build this kind of encoder-decoder. So you will feed in the noisy image and reproduce the correct image without any noise. And if you do that for, let's say, 1 million images, afterwards it will know how to remove noise from images. That's the idea. So it's one possibility of basically allowing you to use a lot more data, because I think we heard that yesterday already. Labeling of data is extremely expensive. You typically need people to do that labeling. And so if you can use these sort of self-supervised or unsupervised approaches where you just make use of the information that's already inside the data and let the network figure it out by itself, you can work with a lot more data, and that makes things a lot more powerful. The other aspect of these kind of encoding, decoding architectures is that they allow you also to change your medium, if you like. So, for example, you can train then models that will look at images and produce text as output, or the other way around. Because you basically, in this encoding vector, you're sort of storing like a concept of things rather than sort of image points or image proportions or so. So it's a bit more removed from, let's say, our understanding what's really going on in this encoding vector. So that's actually a big challenge to get some understanding of what's happening there. But it works. So somehow the network finds some representation of things and will use them then to generate meaningful output. Okay, and here's one example, this denoising, as I mentioned. So for example, you actually, for training, you generate artificial noise, which you add to the image. You feed this corrupted image into here it's called an autoencoder. You somewhat train this layer in the middle there, this bottleneck, and you measure the loss by basically measuring the distance of this prediction here with the original image, and by minimizing the loss, you will learn how to remove noise from an image. That's the general concept. A bit related to that is another architecture, and this is actually, I would say one of the state-of-the-art architectures that's used in meteorological machine learning, the so-called UNet, where it's now a different way of plotting this, but in principle, again, you have this kind of encoder stack on the left. So you have a stack of convolutions. See, the width is getting narrower and narrower, but the length is getting longer. And then you have this decoder part on the right-hand side, reconstructing an image. The trick in this UNet is that you're also copying over some information across each of the layers. So there's these kind of white boxes there, and they're then concatenated with the decoded image. And I must admit, I haven't fully understood the details here yet, but somehow that really helps you to get better reconstruction of the images. And the original application of this was actually biomedical image segmentation. So do people know what segmentation means? I see a couple of question marks. So it's basically this outlining of features in an image. So in medical images, if you have like a tumor or something like this, you want to get the outline of this tumor. And then one more technology that's quite capable, but it has lost a little bit of momentum in the recent 2 or 3 years, are GANs, so so-called generative adversarial networks. So here the idea is, I think there's a very nice description actually in the original paper on GANs, where it's about a robber and a policeman, or forger and a policeman. So there's basically the forger who tries to generate fake images. So that's the so-called generator network. So you feed in random noise and somehow the generator will start producing images from this. At the same time, you then train a so-called discriminator, the policeman, who will try to identify, is this a fake image or a correct image? And basically by training both of them concurrently, you elevate basically both to better and better levels, which in the end allows you to have a pretty good generator that reproduces a lot of the features of the original data. And you can then sort of sample from this kind of feature space. Problem is in these kind of networks that it can easily lead to a so-called mode collapse. So if there's a trivial solution to your problem, then the network has a tendency to collapse to this trivial solution, and that's of course not meaningful. So, but there are ways around that, and there's also combinations then of combining, for example, this kind of GAN network with a variational autoencoder, and then you get around some of those problems. But it can be increasingly complex. Okay, and finally, that's the last one, and we'll touch this a little more in a little more detail in the last part, the transformer architecture. So this uses a concept called attention. Point is here that you basically again have sort of an encoder and a decoder stack. There are also variants of this architecture that only work on an encoder. Main points are on the one hand that you do first a sort of translation of your data into an embedded space. So basically it's a bit like this bottleneck layer in the encoder decoder, that you find a representation of your data that somehow encodes your data. And then on top of that, you add a position encoding that tells you where you are in your sentence or scene or whatever. And this is then fed through the network. And then attention is a mechanism where you basically identify relations between, well, parts of your data. And again, the machine learning principle is that this is learned by itself. So you're not telling the network where to put the attention on, but this is actually what the network finds out by itself. So the origin of this is language processing. And just by feeding it millions and millions of sentences, it'll sort of learn to basically understand language in the sense of which words are related to each other, which belong to each other, in which context. And this has actually been proven very, very successful, and is sort of the new hot thing in machine learning. Right. And I think this is it for part 3, exactly. So are there questions to this sort of really crash course? I think you've all landed against the wall by now on machine learning concepts.
These groups of machine learning, some are like more fit, you know, for weather prediction forecasting, some less.
Yeah.
Is there comparison papers or review papers?
Not really yet. We're not at that stage yet. So there are a couple of comparisons of individual methods. So for example, we've submitted a paper ourselves where we compare a sophisticated model for video prediction that consists of a GAN, variational autoencoder, and something else, I forgot, together with a sort of relatively simple convolutional LSTM network. So that's a network that combines basically this convolution stack with a long short-term memory cells. And the idea, the general idea seems to be a bit that in, let's say, modern machine learning, you use that a bit like a Lego system. Yeah, so you have these elements of architectures, and you can sort of plug them together and build networks in this way.
There's a question online.
Mm-hmm.
I have seen some methodologies, mixture of machine learning and object-based image analysis. Do you have any comment about it from Chiara, who does?
Okay. Object-based analysis, not really. I mean, I could for satellite images. Okay. Yeah, not really. That's not really my field with the satellite image analysis. There would be more land cover classification type strategies. Yeah, but in principle, of course, you can use some of these approaches that I described in terms of this image segmentation. Yeah, so where you define these outlines of things, of shapes in these kind of different concepts. All right, let me switch to the last part. My screen. Okay, I'll let you breathe and I'll take a sip of water in the meantime. So now finally get serious. So what I promised you in the beginning, the application of machine learning to weather and climate, this is what we'll talk about now. So thanks for staying on until now. I'm presenting you some glimpses into current research into deep learning for air quality, weather and climate, actually primarily weather and climate. It's actually amazing. This field is really exploding. So, I mean, when we started our research group in 2018, there were hardly any papers in this field. So it was really mostly rather primitive stuff with feed-forward networks, analyzing some time series from mostly individual stations. And a few initial attempts of doing something like convolutions, but that was really it. And by now there's almost, I would say, almost a new paper every week or so. So there's really lots of groups now working in this and trying all kinds of concepts, and some of them quite advanced already. So as an, let's say, introduction, let me start with a paper that caught a lot of attention last year, Ravuri et al. In Nature. So this was about precipitation nowcasting. So I told you the difference between forecasting and predictions. So nowcasting is really forecasting on a very short time scale, so a couple of hours really. And that's what typical people use for precipitation. Because precipitation systems are so difficult to forecast on longer timescales, it's a bit decoupled from the normal numerical weather forecasting. So you will not run a typical weather model to do this kind of nowcasting for a few hours. But typically what weather centers are doing until now is they have some statistical methods, partly from image processing, that you would simply sort of advect features. So you would try to identify image features and advect them along the image. Or some other statistical methods to basically do this kind of forecast. And through the Ravuri method, they basically came up with a machine learning approach to this. Did I actually mention what kind of architecture they used? No, I think I didn't. Right, and in any case, what I found interesting is they actually showed these results to operational forecasters. So these people that stare at weather maps every minute and then try to digest all that information and really evaluate and then make a decision in terms of, okay, I will issue a warning or not. And they found this really helpful and superior to most other methods they've been using in the past. So it really seems to have worked pretty well, although it's also still not perfect.
And how far in the future do they?
This was up to 90 minutes, I believe, or maybe 120 minutes, but yeah.
So the extremes are a problem, I guess. The observations, you see like dark rock spots that don't appear in the short profiles.
Yeah, exactly. But at least, I mean, and right, and now remember again, I mean, they did actually make use of this kind of GAN structure, which helped them to generate something that at least has sort of features. I mean, they're not red, you won't see the red spots, but at least you see these clear greenish yellow features, which many of the classical or older machine learning methods, in particular something like conv-LSTM or so, did not reproduce. And that's exactly this aspect that I mentioned earlier in terms of the statistics that you use for optimization also. So if you look at the RMSE, then the best forecast would probably be just a mean field, without any features, but of course that's completely meaningless. So you want something that reproduces features, and so if you actually include, for example, this anomaly correlation coefficients in the training as a skill score as a term to minimize, then you can actually generate much better results. Okay, so structure of this lecture will be going through a couple of key papers that appeared in recent years. So the first one is a multi-layer perceptron attempt by Peter Düben and Peter Bauer in 2018. Then we have a paper, Share Missouri 2019, who used a convolutional autoencoder-like infrastructure. Then the UNet was basically introduced by Wayne et al. And then a paper that really created a lot of attention is the so-called ForecastNet paper by Patak et al. I believe that's the one that you, Tom, were referring to. And in order to understand a bit better what this ForecastNet is doing, I will tell you a bit more about transformers, particularly the BERT infrastructure, then the step-2 vision transformers, and also Fourier neural operators, which they made use of in this ForecastNet. So 4 actually comes from Fourier. And finally, I will tell you a bit about a project we're involved in together with University of Magdeburg, which is about atmospheric representation learning. It's somewhat related to what ForecastNet is doing, but I would say on a somewhat more systematic foundation. And then at the very end, I'd like to give you a little bit of a glimpse or just some ideas of where the field could go and what could be tackled with machine learning, particularly deep learning, that cannot be done in the classical setups. Okay, so coming to the first paper, challenges and design choices for global weather and climate models based on machine learning. So basically, Peter and Peter have analyzed a couple of aspects in terms of how machine learning could work and would work for the forecasting problem. They used a relatively simple MLP with 4 hidden layers. Had a global network that would be covering the whole globe. And then local networks with the so-called stencil sizes. So looking at neighborhoods of the point of interest of 3 by 3 or 5 by 5 or 7 by 7 or 9 by 9 pixels. And the data was a relatively easy forecasting problem. These are the geopotential fields at 500 hectopascal from a European reanalysis in 6-degree resolution, so rather coarse, which meant they had 1,860 grid points. And just in terms of understanding the next couple of slides, there's a slight difference between two, basically the same field, but it's sometimes expressed in different units. So you can either use it as geopotential, Z500, then it has the units meter squared per second squared, or you can basically multiply the acceleration due to gravity, then you have the so-called geopotential height, which is then, of course, expressed in units of meters. And that's important because different papers in the series that I will go through have used different metrics, and that, of course, makes it difficult to compare. Okay, so what Düben and Bauer found was that the machine learning, that's these are different approaches of the machine learning with different stencil sizes, was not always stable, so which meant that but with increasing lead time, some of these systems, in particular with the larger stencil sizes, would just explode. So the errors would become really huge. But with small stencil sizes, it would work reasonably. And they also found some ways of fixing this kind of instability here. Honestly, I forgot the details, what exactly they did. I would like to mention that here you see the L1 forecast error. So this is not the most often seen RMSE, so root mean square error or mean square error, but the basically the absolute deviation. They had a reason for that, but it's just a bit, let's say, uncommon in terms of the machine learning literature. This is basically how the fields looked like. Some examples. So you would see the analysis after 24 hours. So that's basically the truth. And in comparison, then the machine learning result. You can see that it captures many things reasonably well, but it's definitely not perfect in terms of reproducing the patterns. And if you look at that again with an L1 forecast error and compare it to normal numerical weather model results, then you see the local NN as the black curve. So that's the one that used stencils. The global neural network is the red curve. So that's the worst one there. And then we come back to this kind of skill score thing. So persistence is the green curve. So that's kind of the thing that you definitely want to beat in order to make anything meaningful. But you also see two other forecasts from numerical models. So the T21 forecast, which is roughly similar resolution as the machine learning model, still has a lower error, so it works better. But of course, it has a lot more processes included than just a simple neural network. And the operational forecast that you see down here is much, much better. Now, I plotted the star here just as a reference. So here I basically did some conversion from the L1 error to the RMSE. So that's roughly what you would expect. And we've done actually some analysis on the error 5 data to sort of see what would be the scaling of the error, basically, if you want to use a metric that's more common in other papers. Okay, so that was sort of the first one that really looked into reproducing somehow atmospheric fields with machine learning and doing forecasting. Next one then is the Scher Missouri paper, who used different complexity, right? Let me just come back to that. So they had different study objectives. So they really wanted to find out how the skill of the neural network depends on the available amount of training data. So how much data you need to feed into the model, how it depends on the complexity of the underlying climate model. So they actually use climate models rather than weather models, and under which conditions it may be possible to make stable climate simulations with the trained networks. So their focus was more on climate rather than weather here. And they used two climate models to generate the training data. So Puma is a model that's used in Germany quite a bit. Plasm, I'm not so familiar with. Again, relatively coarse resolution. T21, T42 means roughly 6 or 3 degrees. Yeah. And then the network architecture is this convolutional autoencoder-like structure. So they had an input of 40 channels with 2048 pixels. Then 2 layers convolutional 2D with max pooling, and then again 2 convolutional layers with upsampling. And the output was forecast for the 800 hectopascal temperature, and then this geopotential height at 500 hectopascal. And then they applied training for 1 to 800 years to basically find out about the amount of input data they needed. Is actually an animation or not? Yeah. So here's some animation of patterns they produce. So on the top again is the truth, on the bottom the network prediction. And you can actually see that this already works visually at least quite well. If again we go to some more detailed error analysis, you see on the bottom the RMSE error and the network forecast correlation. So there's this kind of ACC, anomaly correlation coefficient. And you can see that there are, I mean, where you see the strongest gradients in the field is also where you get the largest error in the forecasts. It doesn't tell you that much if you're not familiar with the kind of numbers of these forecasting errors, but let me assure you they're still relatively large. And this is seen here now, where we compare, again, sort of different setups with these climate models. I need to actually orient myself again through this. Right, so the best model is apparently this purple line, the Plasm T42 with some regridding done. But you can see if you compare it to the Bauer and Düben-Bauer study with this conversion that we applied, it's actually similar. So it wasn't really that much progress in terms of the quality of the geopotential height error. Right, and the dashed lines were, I forgot, unfortunately, right. Yeah, so unfortunately, this paper did not include a comparison to an ODE model itself, so the classical weather model, so it's a bit hard to evaluate, but by making this link to the Düben-Bauer study, you can see that it's still not that great. One thing they evaluated was the evolution of the error with forecasting time, so how many training years they used. And you can see that this actually goes down very quickly. So I think with something like 50 years or so, you can already get a pretty decent forecast, and afterwards progress is really, really slow. Which could, to some extent, also depend on the network architecture. So if you have more complex, more deeper architectures, you may make use of more data. And this is with the same thing for a different lead time here, but you basically see the same kind of thing. Okay, next study by Wayne et al. They, on the one hand, used this, introduced this UNet architecture, and on the other hand, they also basically used a different grid or representation of the data that they found was more amenable to machine learning systems, and the so-called cubed sphere. I will briefly explain that. But first of all, the outcomes of this study are first that an offline volume conservative mapping to a cube sphere grid. Yeah, that they did that, and it seemed to work. That they had an improved DNN architecture, the UNet. And then the other thing they applied, which was useful, was a minimization of the loss function over multiple steps in the prediction sequence. So looking at several output steps at the same time. So not just focusing on T plus whatever 6 hours or whatever, but having several steps in the same minimization procedure. Now the grid they applied is this sort of so-called cube sphere. So it's basically like if you have a kid in kindergarten or so, and they're building their dice with out of paper. That's the same kind of concept. So you basically have select sort of 6 portions of the sphere, and basically put them into this kind of cube model, basically. And then you can feed these individual squares then into the convolution layers.
Why not you use the discrete hexagonal grids?
Well, they just didn't, and that's partly because in their institute, they're also pursuing this kind of cube sphere approach for a classical numerical weather model. So that's why they were interested in using that architecture. Right, and then this is the UNet architecture, which we showed that to you earlier. So with this extra element of copying over information from the encoding to the decoding stack. They had altogether 4 variables that they predicted. So the 500 hectopascal geopotential, 1000 hectopascal geopotential, the temperature difference between 370 hectopascal and 2 meter temperature. They made use of 3 hourly data. So the network was forced to learn the diurnal cycle already. And they had a 2-degree spatial resolution. So already much better than what Düben-Bauer had. And then the sequence prediction, as I told you earlier, basically looks at 2 time steps at the same time. So the loss function has here basically the 6 hour and 12 hour together, or the other loss, then the next one would have 18 and 24 hours together. So it's a multi-step loss function. And they said that more than 2 would actually lead to overly smooth forecasts. That's an observation we also made ourselves for using this video prediction model as a forecasting model. So it helps to focus a bit, but have more than 1 time step in the for the optimization. And then this, I think this is static, not an animation. Yeah, no, it is an animation, right? So this shows you a bit the comparison now between the dense layer neural network model, the verification, and climatology on the right-hand side. So yeah, so it clearly is much better than climatology, captures several aspects of the real forecast, but is not perfect. And again, a bit more quantitatively here. So you see the 4-variable net is this blue curve in the middle on the left, basically, compared to the Düben-Bauer star, and therefore also the Scherer-Wuri approach. This is definitely a significant improvement. And you're now in between sort of two, let's say, reasonable model resolutions. So T42 at something like 3 degrees and T63 at roughly 2 point some degrees, 2.2 degrees or so. So in between that is where you find the machine learning model. So compared to a real weather model with the same resolution, it's worse, but it's already something that could be used in practice. And also here they're showing the ACC, which again is actually, yeah, not much better than the Corsa resolution model, but at least reasonable. So it's not completely bad. So I would say this is actually the first time that a deep learning model produced something that could be seen as a working weather model. Given the fact that weather models were developed over 30 some years, and this has been done in like 5 years. That's considerable achievement. And also, of course, we'll come back to that at the very end. The computing time for this kind of neural network model is much, much less than for the numerical model. Yeah, that's just for 2-meter temperature. Let's skip that in the interest of time, but you find similar results, so it's somewhat workable. Okay, now we get to the current, the probably strongest model, ForecastNet. So whole lots of people from NVIDIA and others who've come together here. So they basically say that they're running a model at 0.25 degree resolution. So that's rather fine. That's really at the range of operational weather forecasts. It's completely data driven. And so for the first time, they can actually make a direct comparison with a high resolution IFS model from ECMWF. And when you look through the paper, at first you're really stunned and amazed. So this really looks great. So in particular, if you look at the center images here, ForecastNet and Truth, this really looks very similar. You can even see something like a hurricane showing up here. This is also shown in the details. Yeah, different typhoons, hurricanes are visible. So this is quite impressive. I guess I've talked to some of the people at the Weather Center in particular. I mean, they still see a couple of deficiencies in the ForecastNet model. So the claims they make in the paper are not fully fulfilled, but it's definitely a pretty large step forward in the right direction. And they've been using this transformer architecture with some retraining then for, what they used in training is the, let's say, large scale dynamic variables like this geopotential, temperature, pressure. And then they did a retraining for example, precipitation forecast. So just the final layers were retrained. And then you can see that also for precipitation, it actually does a reasonable job. It might not quite beat the Wuri on short time scales, but here the point is that this is a precipitation forecast for longer lead times, so up to 36 hours.
I see the lots of these machine learning examples. You show the, you just show the image.
Yeah.
Right, but I'm curious, like, what is the accuracy of the weather stations that they have, like, measurement?
And that's part of the big criticism that they don't fully evaluate their system. So I mean, I showed you these plots with RMSE or ACC, but that's as far as they typically go. And that's exactly why I made this lecture on statistics and how to evaluate a forecast properly, because that's not yet done in the world of machine learners. So.
Yeah, I'm looking at that paper and when accuracy plots,
Mm-hmm.
they only have
Yeah.
comparisons.
right? I mean, there are a couple of things here. So at least they're looking at ACC, which is good, but of course that's only part of the story. So and here you see like for 10-meter wind and for TP was exactly, I forgot, 2-meter temperature, geopotential and so on. And here they claim that they're actually partly better than the operational IFS model. Right. And they also compare to this Wayne study, against which they're clearly much improved. Yeah. All right, now let's look a little bit into the architecture of this thing, because in principle, I think they've done the right move by going to these transformer architectures. So in principle, what they do is they have their different atmospheric variables as individual fields. You can basically consider them as a stack of images, if you like. Then they're cut out in patches. These patches are embedded into some sort of information state. I will come back to that, plus the position embedding to tell you where this patch is. And then they have this so-called mixing, so in spatial mixing and channel mixing, which is this so-called attention network. And then again, they decode to make the forecast. And in between, in this mixing stuff, they basically use this Fourier net thing for, I will come back to that. And then on the right-hand side, you see 3 different applications. So basically what they did first is for the normal forecasting problem. That's really just the inference. So that's basically just the plain base model. So 2 of them stacked together. And then for the precipitation, they basically kept the backbone and then added a precipitation model on top. And then for fine tuning, you can also rerun basically retrain just the second of these models. Now, to make it a bit more understandable, we'll look a little more in detail into transformers, also vision transformers and the Fourier neural operators. Again, this will not replace a full lecture on these things, which can probably take days, but just to give you a couple of the general concepts. So the main thing, and this was really a big breakthrough in language processing of these transformer models, was coming from language translation. And the idea is that instead of these sequence models that had a fixed length, you could, with these transformers, build variable sequence lengths. And you would really just paste everything together. So you would not stop at the end of a sentence and say, this is what I look at, but you would really take into account longer text passages. And these are then separated by separator tokens. And also you have these so-called class tokens that kind of give you a classification of the sentence, basically where it belongs. And then there's some other special tokens, like, for example, playing. So it's really not words directly, but more something close to syllables, basically, that are used as the individual token. So you break your sentences into these kind of tokens. On top of that, you add, in this case, actually also a segment embedding. So you make clear to which sentence basically these things belong. So there's just basically sort of a number added to the other stuff. And then you also embed the position of where this is in the sentence. And the key idea of this embedding is that you find basically vectors in a high dimensional space. So typically the space is around 512, can also be sometimes 1024 or so. And you basically optimize the vectors or the embeddings in a way that things that belong close together are nearby each other, and things that don't belong to each other are as far apart as each other as possible. And that's in a vector space. This is basically the angle between the vectors, which you can get from just the dot product. So that's a key concept of this embedding. And so here I'm drawing some examples in only 3-dimensional. I still have a hard time drawing 500-dimensional vector spaces. So that, for example, bicycle and mountain bike are very closely related concepts, so they should appear close to each other, whereas something like a train, well, still has some relation because it's also some mobile device, but it's, of course, not a bicycle. Whereas something very different, like chocolate, will point completely elsewhere. Now, the key point is that this embedding is also something that's actually trained by the network. So you don't impose the embedding. So you don't come up with an algorithm how to translate, for example, bike into a vector. But this is something that the network figures out by itself. So that's basically the first thing that's learned. Right, and then one important aspect that also made BERT so successful. BERT is one of these or let's say the fundamental model that first implemented all this was the training strategy. And this is also something that has by now taken up a lot of attention, is masking of the sentences. So, for example, the original sentence is "let's stick to improvisation in this kit." You would just randomly mask out portions of the sentences and let the model reconstruct those. And that's the way how it can learn these relations between words, but also which words are missing and where they belong. So that's the key training strategy. Right, and you see then that, for example, there's a list then of the possible classes. So these class tokens are all English words, and you can see that basically at improvisation you get the maximum likelihood, so that the masked word is with 10% chance it's improvisation, everything else has a lower chance. And for example, if you use Grammarly, this will almost certainly make use of this kind of architecture, and then you can of course get not only the top one, but you can also look at the second most likely outcome and so on to get you some alternatives. Right, and then these attention layers. I think I don't want to go into detail here. This would take too much time. But in principle, you're then comparing the vectors of an input sequence. So if you have something new that you show to the network, that your query basically with the outputs as key and value basically, and you do this with a matrix multiplication, you do some scaling, you do some masking and a softmax, and then some other multiplication, and that's basically how you derive the so-called attention between two tokens. And this can then be done with multiple heads, so you can basically break the sequence into chunks. And then have multiple of these attention layers work in parallel. And then again, they're stacked together vertically. So that's kind of, in a nutshell, the architecture. This definitely requires more in-depth reading to understand that. But here's just an outcome of how these attentions could look like. This is now from two different levels. So at the lower levels, you will find attention between neighboring words. So in this case, the sentence is "the law will never be perfect, but its application should be just," and so on and so on. And you see that the attention is really only relating words that belong closely together. So "the" and "law" and or "will" and "be" or so. So it's really in a very narrow local environment around a word. Whereas then in the deeper layers, and this is a bit similar to this like image recognition in convolutional networks or so, you will find attention between things that are further apart. And this is basically how the system can sort of understand the structure of sentences. Yeah, so you will find a relation between law and even here, like, well, the end of a sentence doesn't make so much sense, but whatever, some others, application and whatnot. So these are longer scale structures. Problem with this kind of attention mechanism is that it scales with the quadratically with the number of tokens you basically put into your focus. And then there are some techniques that have been developed, like using sparse matrix approaches and so on, to reduce the computational demand on that. But in principle, this is a really powerful way of doing that. And then people in 2021, so Dozovitsky basically from IBM, I think they were, came up with the idea to use the same concept for image processing. And here they basically cut the image into patches, and each of the patches was then embedded into these kind of tokens, so very similar to words. just that the input is now images. But I mean, for a computer, it doesn't matter at all. So for a human, a word and an image is something completely different, because one goes through the ear, the other through the eye. For a computer, it doesn't matter at all. It's just a sequence of bytes. Yeah, so, and that's basically the main thing here, that you get independent of the type of your input data, as long as you find some sort of embedding that represents your information. And again, you will have that positional encoding, and then this transformer encoder on top of that. And oops, that should, yeah, animate. So this is then from one study further, I think, where they did that also for video processing. And you can see here on the left-hand side the actual image, so an ape swinging around in the branches. And on the right-hand side, it's the attention maps. So basically, everything that's colored is what the network looks at most carefully. And the main thing is that this network has not been trained to identify objects. Yeah, so it wasn't a purpose of the training, but it was done through masking and other things. But nevertheless, the attention focuses on the object. So it basically automatically identified objects in this video and was able to track that pretty closely. So that's kind of a key to success. And in a way, this explains a bit this concept of representation learning that I will come back to in the end. Where the main idea now is these days to somehow train a network to find a representation of the information that you feed to the network, and then use that representation to do all kinds of things with it. Yeah, so once you have learned that, in particular these kind of architectures, you can then apply it to either do a translation or like a scene description. I mean, you may have seen that in YouTube sometimes, that there's an automatically generated text below the movie, what this scene shows. And that can be generated through this kind of concept where you have a representation and then you basically retrain the output to generate text instead of an image. Right, and then neural operators. I guess I have to be really brief here, partly because I have to admit I still don't fully understand them myself. The main point is in neural operators that you're not training basically individual samples, but you're basically trying to learn a partial differential equation. Basically, you try to learn a function. And this makes it powerful in the sense that you can much better than, of course, extrapolate and yeah, if you're kind of reasonably sure that you learned the right function, you can kind of better interpolate and extrapolate in this function space, and you won't get this kind of overfitting in the sense that you just learn the specific features, but not a relation between data points. Right. Yeah, I guess I'll really skip this now. As I said, partly because I don't understand it myself. Okay, just some examples. They applied this to a Navier-Stokes equation. So this is artificially generated data, but then you could use that very easily to very well to reproduce the prediction. And the point is, and this is just a very small excursion to this so-called physics-based machine learning. So there are other approaches that try to learn PDEs, like so-called PINs, physics-informed neural network. But there, you basically have to retrain the network for every change in your parameters. So if you look at the Navier-Stokes equation and you would use a different viscosity or something else, you have to retrain the network. It gives you a completely different set of equations. In the Fourier operator, sorry, in the neural operator setup, you can use the same network to generate predictions for all kinds of, for the entire parameter space, because it's learning the underlying equation and not the state, basically. So that's the main concept. In this forecast net, they've used this kind of thing, and basically as a so-called Fourier neural operator. So here they basically describe a Fourier series, which you can use to describe all kinds of wavy patterns. And you may have seen in charts or satellite images of the atmosphere, that typically very often you see these kind of wave-like structures. So Fourier is a good attempt, and it's actually also used in weather models, Fourier series. So learning a Fourier series of your phenomena seems like a good approach, and that's basically what they do. Right. Yeah, and somehow they transform these tokens into Fourier domain and then sort of optimize them and so on and so on. Right, and that's what they do. Yeah, let's skip that. Right, and then, okay, so and then finally, our ATMO-REP, so atmospheric representation learning, has many similarities to this forecast net, except that at least until now we are not using neural operators. So this is a predecessor step of that, where they also used sort of a attention network, so-called CMA's representation network, with two different scenes. And here, and this is one aspect I'd like to come back to. The pretext task, as it's called, was to predict the time that passed between the two scenes. Yeah, I told you earlier in the BERT network that the one fundamental aspect of the success of that architecture was this masking of words. And you can do the same with images, of course, that you mask out regions. And here what they did is a different task. It's basically trying to teach the network to find out what's the time difference between two scenes. And again, that basically leads to this representation in the feature space, where things that are similar should be close together. And in the end, they could do reasonable predictions with that. And then if you evaluate that, it's quite kind of interesting to look at that. And this goes a bit into explainable machine learning, trying to understand what's going on in the network. So you can kind of see that the signals are basically driven by what happens over the continents. And whereas the ocean surfaces don't give you that much information. And here's an example as a downstream task. They then use gap filling. So now they took out like a square in the middle of the scene and tried to reproduce that. That's a bit blurred here. But basically the ground truth, you can see this kind of feature running there diagonally. You can sort of, if you want to, you can sort of see that in the ATMO-DIST network. It's much harder to see in the other techniques that were applied here. So kind of shows you in principle it works, but it does decrease the signal strength, just as we also saw from the Raburi paper at the beginning. And I will be done by then, I'm sure. Okay, because I'm now reaching the final slides. Are there any questions up to that point? Yeah.
Yeah, the question. A lot of papers you mentioned before, they use the 500 hectopascal height of the atmosphere. In their models, is this linked to physical attribute of the atmosphere, like a viewpoint or something, or is it more like a random number they choose?
Well, it's not random. I mean, it's sort of a variable that kind of describes the large-scale state of the atmosphere. So, yeah, right. And it's sort of, I mean, the large-scale weather systems, they're sort of governed by what happens there at the 500 hectopascal level. And this geopotential will sort of show you a bit like where you find the high pressure and low pressure systems and how they move and this kind of stuff.
Because they also use like the 800 hectopascal level. Yeah. So there are other things happen in this height.
Right. Yeah. And in general, you can say, I mean, based on, I mean, the surface is what makes it completely very complicated. Yeah, so this is also when you develop new weather models, you will first use a so-called shallow water model, which basically has just a naked Earth to just get the governing equations right. And this is somehow still reflected in the middle atmosphere levels, middle troposphere levels, around 5 kilometers, 500 hectopascal. What happens close to the surface is really messy and noisy, and because of all the things going on at the surface. And so that's why also for like training machine learning models, it's best to start easy, and then progressively you want to get down to the layers where it really matters for humans. That's in a nutshell. Any other questions? No, then let me wrap up here with some things or ideas where we want to go. So the first thing is clearly, I mean, this what I showed to you is already quite big. So I mean, this forecast net has, I forgot, I think it's 27 million parameters or something like this. So it's already a pretty huge network that needs, of course, a lot of resources to train. And clearly there's room for more. So you can include more variables, more levels, finer resolution into the networks. But of course, the issue then becomes the training resources. So these networks really take, I think for ForecastNet, they reported somewhere it's like 4 days or so that they needed a supercomputer to train. That's quite a bit. Another big question, and I think that's actually very interesting to further think about, is physical constraints. And the question is, to what extent do we actually need them? So ForecastNet does well without any specific physical constraints. I mean, I told you that they use these Fourier neural operators, so there's at least some, let's say, physical thinking in what they do, but there's no explicit prescription of the model needs to follow this partial differential equation or something like this. So in that sense, there is no physical constraint. And the question is indeed, I mean, how much can you gain? I mean, do you make your network better or perhaps even worse if you include these physical constraints? Because you may sort of, if you do that, you may force your network to pay too much attention to something that's only approximately correct. And so you may miss out on the last little bit, which is really the interesting part, basically, that's in the data. Another big topic for the future is climate prediction. So most of what I showed to you is really more on the weather timescale. In climate predictions, of course, you have to deal with this context drift problem, as it's called in machine learning. So clearly, I mean, if you look at global warming, you get a bias that increases. So if you learn the state of the atmosphere today, or the relations between atmospheric variables today, they may be different in 100 years' time from now, just because the system has evolved into a warmer world. And so that's something, again, where potentially we actually need the physics in order to be able to come to grips with that. And another thing where I see a lot of potential that hasn't really been tapped so much on until now is the direct use of observations. To your question, Tom, earlier I answered that indeed data assimilation is one of the application areas where machine learning is used. So in only the data assimilation step, yes, they're doing this, but basically in a, let's say, complete forecasting system, this hasn't been done yet. But all the studies that have been done so far are always trained on already modeled data. Yeah, so no one has dared yet to directly process satellite data and make a prediction based on the satellite data, for example. Another aspect I'd like to mention again, and we've briefly discussed that, is indeed the evaluation of the forecast. And so here I'm just referring to sort of standard literature from ECMWF. They have this evaluation guide or upgrade, and this has like, I don't know, 100 or so pages with, for example, score charts like this. A little hard to see on the beamer, but you basically see for every variable on different levels and different forecast lengths, you see these different metrics here, like the anomaly correlation and the RMS error. And you can basically then evaluate. For them, it's here most interesting to see the update of the forecasting system. So whether the new forecasting system gets better than the old one. And you can see some things have gone down in quality, others have improved. But it's really a pretty thorough evaluation in terms of capturing many aspects going on in the atmosphere. And this is what we don't see in any machine learning study. So this is really room for improvement to do a more thorough job. Right, and then at the very end, computational aspects and benchmark data. So I just copied out from 2 of the papers I showed you. So the Wayne study and the Patak study. So Wayne said after a one-time computational costs of 2 to 3 days for training, the model could produce the global 4-week forecast in less than 0.2 of a second at 2-degree resolution. And this is, of course, much, much, much faster than any numerical model could do. And a similar statement in the ForecastNet. So they have a 100-member 24-hour forecast in 7 seconds. If you compare that, like the ECMWF model would have something like about 1 hour, 20 minutes for a 10-day forecast of hourly output. And I think they run a 20-member ensemble there. So that's definitely a huge difference and shows you to some extent the potential of the machine learning, but as of yet, I think we're not there with the quality yet. One other important aspect in terms of the evolution of the field and what's missing or just starting to happen is the development of benchmark data sets. So benchmarking has been, I would say, the fundamental game changer for things like image recognition or also speech recognition, stuff like that, that people, the community basically got their act together and defined these benchmark data sets. And then all machine learners tried to beat the best performance of their colleagues. And to some extent, it has become basically futile. So, I mean, no one uses MNIST anymore except for teaching this simple number data set. And there are now, I mean, the latest versions of ImageNet have something like, I think, 1 billion images that you can train on or use to evaluate. That's really has become huge. And that's something that's still largely missing in the weather world, but it's slowly coming around now. So the first benchmark data set was WeatherBench. And also we have an equality benchmark data set that we produced. There has been in Malmström in the project, there are a couple of benchmark data sets that are being produced. And Peter Düben, myself, and some others have recently published a paper to actually make a claim that these benchmarks are needed and also what kind of benchmarks are necessary or useful in the meteorological field to improve the situation. Right, and there's also a system here, the PanGeo, which we aim for that this will sort of be the repository for these kind of benchmark data sets. We have to see. Okay, final 2 slides in, I think, less than a minute. Just a little bit of a really fantasy in terms of where this can go. And where I see a lot of potential is really in linking, let's say, all these kind of weather phenomena with all kinds of other socioeconomic or other geographic and whatnot phenomena or policy actions and all that kind of stuff, which have been really difficult to tackle in the past, partly because the modeling of weather and climate has been so extremely expensive. So, I mean, you can easily imagine that a decision maker wants to basically play through 100 different options, like whether to build a dam here or a windmill there or whatnot. So there's very easily you can get into a scenario space that's just huge. And you'll never be able to cover that scenario space with traditional models just because they're far too expensive to run. And now having machine learning to do that much, much cheaper with at least reasonable quality might allow you to really play through this real host of scenarios in a much better way and take into account all the kind of weather or climate impacts and then start looking at these kind of combined effects here. So here's just one, for example, increasing heat could also on the one hand lead to stress on the plants, but also stress on the farm workers. And then you can sort of play through options, how to protect them. Or increase your yields and stuff like that. And you can really start diving into these kind of analyses with the help of machine learning, weather and climate models. Or also looking within the system, basically, sort of the climate change system, the physical climate system, ecosystem system, human society, looking at these kind of different feedback processes and trying to figure out the strength of them and how they interact and all that, which I think has been out of reach until now. So that's kind of the big hope I would see for, let's say, the coming decade or so in this machine learning for weather, equality, and climate. Thank you for your attention, and I'm happy to take further questions.
Why do you think is it a question mark to involve physical relationships in the modeling approaches for weather forecasts is so big, like compared to maybe hydrological models, they really would like the core of hydrological modeling. I think including physical relationships. Maybe weather forecast random effect is much larger. Or...
Yeah, it's primarily it's the aspect of the unresolved processes. So I mean, if you have a gridded type of model, You always have a limitation of the resolution, what you find. And as I showed you, these scales in the atmosphere, they really range from centimeters to hundreds, thousands of kilometers, and you will never be able to run a gridded model at a centimeter scale. I mean, even energy-wise, that would be prohibitive. So therefore, there are always processes you need to leave out, and you need to somehow parameterize and make some estimates in terms of how they work. And they can play a big role, basically, in the evolution of the system. And if you constrain your system to follow a physical equation, and you have sort of some unknown processes that affect that, this can be partly a scale process. So, for example, I think we mentioned that in the coffee break, like a small valley or something like this, that's just not in the model. This cannot be represented in the model, but it leads to a bias in your prediction versus the observation. Then basically the model will never be able to capture that if you have the physical constraint. If you don't impose a physical constraint, it may actually see that, yes, there's something going on, so I need to correct the bias here. That's just in principle the effect why it can be actually detrimental to use physical constraints. It can also be helpful. That's I guess it's still an open question.
Is there any rumors, or just out of curiosity, any talk in the atmospheric prediction realm on quantum computing and how that might evolve, and when it becomes available, and what that might bring to the table? Because I think that would reduce computation times quite
tremendously. Yeah, I mean there clearly is, but I'm not an expert there. I mean we do even have a quantum computer in Jülich, but that's not my cup of tea. I still find that rather weird what's going on there.
This forecast net,
Mm-hmm.
is this data simulation, right?
It's not data simulation. So they've also trained on model data from the IFS model. So it's not using observations, but
Recalibrate. It's not recalibrate.
No.
Just make it once and believe.
Yeah.
Okay. Because I thought they said adaptive Fourier neural operators.
Yeah, but that's just this adaptive thing is just the way they construct their Fourier neural operators, that they can still sort of, they change over the course of a training.
And your experience is there like cutting edge in data. That's not good.
That is pretty much cutting edge what you find right now. Yeah.
But they only did it to 30 kilometers enough, like fine resolution.
This was 0.25 degrees. So yeah, right. That's roughly 30 kilometers. Yeah. 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 Well, again, I mean, the point is that if you want to go finer resolution, you would have to either combine a number of regional models that run on finer resolutions, or make the big step to directly using observations that are available in finer resolutions.
There's a difference in like weather forecasting, like extreme events and just like a standard weather, you know, probably there's the big differences. Because
well, it's not really a big difference. It is more that, I mean, extreme weather, of course, is part of the weather prediction, and one that has generated a lot of interest in society, of course, for obvious reasons. You will not be able to construct a system that only predicts extremes. That will not work. Yeah. But indeed, I mean, the extremes, and that's, I think, one of the criticisms also of that ForecastNet paper. I mean, they have not done a thorough evaluation of how well extremes are captured. I mean, they show these images that, yes, in principle, they can see typhoons or hurricanes, but I mean, whether they are following the correct track or whether they're in strength roughly decent is not really shown.
And just a question, in which programming languages your group works?
My group is pretty much exclusively using Python. And I believe that's for most of the kind of weather-related systems. And there are these two major frameworks, so TensorFlow and PyTorch, and I would say it's about evenly divided. But there's a tendency of the community to go more and more towards PyTorch.
And you use HDF as a data input output?
It's different. So the weather community actually has a special format yet again called GRIP, which unfortunately is completely incompatible with anything the machine learning libraries use. So typically there's some translation processes needed. So usually first to NetCDF, and then either you directly use the NetCDF data or you convert it to TensorFlow again. Yeah, and that's quite massive data handling. So
And how do you visualize spatial data? Do you use QGIS or?
actually, no. That's one of the things I always find very interesting, because I actually think that the GIS systems have a lot of power that's completely underused in the meteorological community. So they're typically separate viewers for these kind of meteorological data. Also, again, very often written in Python.
Okay. So just especially just for weather.
Yeah, and there are some reasons why this is so. In fact, I've been discussing with some people from the geo community on that, but they never really picked up on that. So one of them is the vertical coordinate system. So I mean, typically geospatial data just has the surface or then meters like altitude, but you can't deal with these kind of pressure levels and this kind of stuff. So that renders it irrelevant for meteorological data. And the second thing, at least until recently, I think this has improved a lot by now, is the temporal component. So let's say 10 years back, when I looked at it a bit more in detail, it was basically almost impossible to follow things over time. It was really more like static images. And
use Google Earth because it can visualize the 3D, 4D, whatever.
yeah, no, hardly.
No.
Yeah.
And, like Google Earth engine.
Some people use it, yeah, but it's really mostly for the satellite analysis, not really for the actual weather data. Yeah.
So your group never uses Google Earth engine?
One of my PhD students used it, but to get remote sensing data.
Just to extrapolate.
Primarily to extract the remote sensing data, yeah. But that's actually one thing I would see still a huge potential. I mean, if basically there would be a bit more, let's say, collaboration between these communities, and some of the GIS techniques or so would be used in weather forecasting, that could do some nice things, particularly overlaying then these different layers, like weather layers with topographic layers and so on. But I think one aspect for that would be that GDAL would need to be parallelized, so that you can do much more efficient access to the and conversions of the data.
The parallelization in GDAL, but for compression, but you can tile and then you move in GDAL processor and combine again.
Yeah, but I think it would be worthy of a larger project to sort of tap into that kind of connection.
Okay. Any more questions? Yes, we have to slow.
You talked about earlier doing walking for this kind of temporal autocorrelation. In this area, how is the spatial autocorrelation like dealt with the kind of test trains?
Okay. Very good question, actually. So I guess in the type of application that I showed you, it's mostly that you're trying to do this kind of field forecasting. So in that sense, it doesn't matter because you treat it more like an image. Yeah. Of course, if you have other applications, and for example, one study we did is a mapping study where we try to extrapolate ozone concentrations from individual measurement stations to a global map. Then that matters. So, and particularly it matters for the evaluation. So if you want to evaluate your mapping skill, you don't want to look at two neighboring grid boxes basically to evaluate it, but sample them accordingly. Yeah. And in terms of forecast evaluation, so coming back to part 2 of the lecture with all the statistics, that's indeed, I mean, a pretty challenging problem to tackle the spatial correlation. And you almost get me to start talking for another hour or so just on on the modern trends in statistics, which are okay.
Yeah.
So we should sit together at lunch. Yeah. All right.
Okay, we'll be like lunchtime. Please come back 1:30. We have here ESEP Eversman talking about ESEP at the time and starts.